So welcome everyone to the 53rd concurrent session for the International Association of Energy Economics online conference for 2021. My name is Kelly Burns. I'll be chairing the session today and will also be one of the presenters. We have 3 presentations in total today. So each presenter will be allowed approximately 20 minutes as well as a 5-minute Q&A time. It's up to each presenter as to whether they would like to receive questions during their presentation or answer those questions at the end of their presentation. I'd encourage everyone to either use the chat facility within the Zoom or to use the raise the hand facility during the Zoom if you'd prefer. Diego is here to assist us if there are any technical issues whatsoever. But I think we have a really exciting session up today. It's all about sort of prices and subsidies in both the wholesale and the retail market and how that's really affecting outcomes for consumers and producers and prosumers. So I think we're going to be up for a very interesting session today. So I'd like to introduce the first presenter. So Fang, you will be talking to us the title of your presentation, who will be the beneficiaries of renewable energy subsidies in China, an analysis from the provincial level in China. So Fang, if you would like to take the floor.
All right, thank you. Do I have to share my desktop?
Yes, if you could please share your presentation in the share screen, and then we'll all be able to see that. That would be great.
Okay. Okay, they ask me to open my system to give some preference. Oh, let me see how to do this. Did you see my screen?
Not yet. Now, yes. Yeah, perfect.
Yeah, that's okay?
Yes.
All right. So this is fine? Is that okay? All right. So thank you everyone, and thank you for the opportunity from the IAEE. This is my 3rd conference from the IAEE community, and I submitted this paper like 2 years ago, and because of pandemic and lots of things changed, and so does my papers. So I switched a little bit of my paper to the different name. It's like first I want to use the Chinese provincial level to study the renewable energy subsidies. Then I switched to like using the club theory to test how to do the abatement in China. And so this is a new title for my paper. It's applying club theory in achieving regional carbon neutral target abatement game in Chinese province. And I have 3 people in the paper. First is me, and the second is Ming Fang, and the third is my supervisor. And I will come in the 5 section of the paper. The first is background, then theory and model and result, and conclusion. So for China experiencing severe climate change problems, and because of the balance between the environment and the economy development. And they have lots of greenhouse gas in the atmosphere, and they have like impact for the temperature change, and that's a lot of stress for the Chinese government to control the carbon and to control to deal with all the environmental changes. And in the last year, the Chinese president of China and the President Xi announced China will reach the peak by 2030 and be the carbon neutral by 2060. Even it seems it was all a little bit late for China, but that's a target we're doing. We're on that road. And it has been a lot of literature focusing on Chinese problems dealing with the carbon. The first is maybe the carbon tax. They have tons of mountains of literatures. And the second is carbon trade, and the third is a clean development mechanism. But for all this, the policy they designed already, it's based on the existing trading system inside of China, like no tax or no punishment for the free riders, who no punishment for the province who pollute a lot. That's just the old that's the older literature based on the old systems. And so in this paper, I gonna use the club theory to test how to improve the carbon emission issues in China. And from the theory part, the fundamental of the climate change is public good of the problems of the public good. The public good, like the climate change, is like you cannot let me all right. So the public good is like from the climate change part is like you cannot, everyone can enjoy it, and you cannot punish people for not contribute to this. And from the cycle of the carbon, you can say the first is like we have the economic growth, and then we have the emission of the carbon, and then carbon doing some physical activities and to reach the temperatures and do the climate change, and climate change to some bad impact, negative impact to the nature system. And then they have another feedback to the economy activities, and that's all. That's the sense. But for the public goods, every province in China, or every nations in the world is doing the same process, but but some people they pollute more, and some people they pollute less. And but the province, the peoples who pollute less, and they have maybe they have less benefit from the economy, so they will switch the strategy next turn to to do more climate harm. So this is a game. So every people want to get their best, but we have to find the best system to control it. And the free riding occurs in the climate change stuff. For in the world, we have lots of the attempts to try to reach some international agreement to to control the climate change. And when we have the Kyoto like agreement in the very early, but the American quit first, and then Canada quit, and every people quit, and it was end like 2013, I think. And then we have another agreement like the Paris Agreement, but it's unstable because everyone can join and live without punishment. Like the American, they quit around last year and they come back in the new Biden's government. So it's really hard for the international society to find a stable collision for the people to really to do good to contribute to the climate change. So with Nordhaus, the people from the Yale, and he come up with the climate club's system to change to control the climate change. And they have some characteristics you wanna share in this club. And it's like we have a club, and we have a sense when we will have to share this club climate. And then we have to people in the club have to, you know, contribute their maybe their the abatement cost and maybe pay some dues. This is for the people in the club, and the people not in the club is like you have to be excluded or punished like the people like you know, if you do really bad in the climate change stuff, and you should be punished. But why? That's it from the club system. And the last important point is like no one want to leave. So this is the sense came from the North Horse. He published this paper in 2015 in the American Economy Journal. And so and this is from the serial part. So for my part, I want to build a model in China and to see if I can use this model to achieve the you know, using the climate club the system to achieve the abatement goal. And first, I will want to take a look at the Chinese decarbonization trends. The left one is for the Chinese one is it's like efficiency, like the carbon emission every year, and divided by GDP each year. It's like the trend is going down. The red one is like from the North Horse, his paper. The word in the trend for the whole world is going down like this, but the trend in China is like more is 3% every year, and for the whole world is 1.5%. And but one interesting trend in China is like this is the right line. It's the trend every, you know, the carbon emission every year. It's going up very fast every year, and this is from the 1997 and to 2017. And but the blue line is like from the temperature. It's not going up very fast. And the red picture, the red picture is from the North Horse showing the world trend of the temperatures going up. So maybe the club can be formed in China because we don't have to take the consideration of carbon issues in the North Horse stats model. So and the third point from China is like we have lots of the, you know, carbon emission levels in different provinces in China. You can see from the different color, it's like the province in the east side and on the coastal side is like they have lots of emissions, but on the west side they don't have lots of things. And this is for the just emissions, and the trend for the different years is like it's changed a little bit. And then but at the same time you can take a look of the GDP. It's like the GDP is all all distribution is on the east side, and the coastal side they have lots. So which means the people they have more money in this side. On the east side, they're sharing the climate goods together, and they have more willingness to pay for the climate change. And this is the third picture I want to show you. Is like the carbon emission intensity in China. And you may say at first in the 2002 they have a, you know, on the east on the west side they have lots of emissions, and but gradually they have some trends like in order to make some more development in the economy. And the west side they're making more pollutions, but with little economy growth. So which can be concluded that the province on the east side they want to make more contributions to make a, you know, better contribution to the climate change stuff. So this is all the basis and the fundamental stuff to build a climate club in China. And because China is like a multi-regions, and which is similar to the nature of the countries in the world, and the free riding in the climate stuff is in China, is very common in China. And and the Chinese carbon emission is varies in different regions. And also the border carbon tariff can be modeled in China province, because we have the different society, we have the different system, and we have large governments, powerful governments, and we can impose all the border tariff very, easily, and together improve the overall welfare of the society. And also, we can use the border carbon tariff to invest in the carbon neutral development, and maybe can give the green funding some money, and to let them to invest in the whole country. And also the people in China, they are getting more awareness of the environmental change. They want to make it change, and so on. So in the model, we promote encouraging the people and to become the members first, and then for some high developed province, and to they form the club in small group and let people to join, and whoever in the club, they can get better. Is they contribute from the carbon tax and carbon price to to control the carbon emission, and for the people who for the province outside of this club, and let them pay the punish the punishment tax if they want to join. And the balance is like, if the province, they can the cost of entering this club and the cost of the carbon abatement, it's the same, then probably they will do the same. So in China, we have lots of province, like we have 32 province, for the data available. And this is a game. This is a game theory. And first we can see, for if the province want to join the club, is he will have a function. The function, like, first is a province output, and second is tariff. He can get it from this province or not, from this club system or not. And third part is like, if he's not in this club, and what he has to pay for the club, and this is abatement cost, maybe it's it's a function of it's a function of the output, and the function of the carbon price, social cost of carbon price. And this is the damage. The last part is the damage part. Damage part means like, how much damage they will make to the whole province, maybe the whole climate, and also I include the health vulnerability into this damage function, which is pretty new. And also I put some the climate sensibility, since maybe some of the province, they have a more dry land, and maybe some of province, they have like they are more sensitive to the climate change. So I mix them into this damage function, and to say this is decision function, one of province want to join or not. And this is some like the temperatures inside of the model. And yep. And this is a model. And also the abatement cost. Abatement cost is like from the whole region. You may see this. The abatement cost is like it's from a few abatements this, and the welfare is like you get the average level of abatements in this whole country, which is moving. It's a moving thing you have to calculate. And the last one, the damage. Damage is like it's your change, and the from the change in one province, and the change in the province other in your province. It's like a game theory. If you join the club, you will get a one welfare functions. You can get the result. And but they also have other province, and every province they are making the decisions. So this, if you want to get the whole result, this is a big function. It's like the 2 times 2, you have to time like 32 times and to get the whole result. I made some so I separated all the province in China into 8 parts, and maybe in the I can't remember, maybe in the 7th part, because one of the, let me see, because one of the province in the Tibet is they don't have they don't have results. So I separated in Chinese provinces in 7 part, and to see what's the benefit, and what's the how many people will join this club, and what's the carbon what's the carbon in abatement, the reduction they can have in this model. And this is the early result from this model. And from the penalty, this is tariff, and the tariff when they are very low and everyone join, and the tariff on goes a little bit up, and they have a, let me see, all right, so if the tariff goes a little bit up, then let me see. Okay, this is a welfare function of the whole regions. And on this side, on the x side is like the carbon price, and this is the border tax for the carbon is from the 0 to 10%, and less people will, they will lost the, okay, so they will lost lots of the welfare, but this is a function like how many people will join, like the higher of the rate border tax, and the higher of the carbon tax carbon price, the more people will join. And this is also a function of the carbon, carbon emission function, and you can see in this the whole of the whole systems. So which means even though we have like a welfare for the whole society for this, it's like it's because including their output, their economy output from this one, from this part. But if we want to make more control of the carbon, it's this function. We have to give like the carbon price, and the right a little bit higher border carbon emission tax. But maybe that we have lots of the laws, like inefficient laws in this model. So probably the best scenario is like around 5% tariff, and the carbon price is around 100. It's somewhere here. It's the most efficient by that time. And this is another scenario, and we want to say it's like first we cannot calculate all the welfare into including the output of the economy. We have to also take into consideration of the carbon, which is can be seen in this. It's the same result, like when the carbon the border tax around 5%, and the carbon price is around carbon price is around 200, maybe 100 or 200. It's around here. This is a tendency how many region will join this system. It's a little bit, every time when I run this model in the computer, it takes around 10 to 15 minutes. And each decision, each model changing, I want to do this model, it takes time. And I'm thinking to do a more, I want to to change my model to make it more efficient, and to get the best, assumption, and to maybe make this model in more detail, and to give I want to say like a mountains maybe on this result of file. And maybe on mountain I will have to think about the economy output, and to leave it somewhere, or make it to some other model. And I want to say a mountain on the top, that's the best time. how many what's the border tax will be and what's the carbon price will be. But this is for me it's like a good attempt from to try to solve this, to try to apply the climate club, the system inside of China. And yep, that's my result. It's not very good so far, and I'm improving that. And so the conclusion for my paper is like first I basically made some discussion on the global climate change, and then I made some did some literature review on the Chinese carbon control study, and then I built up the system, and I make some I found some information about maybe we can build a climate club system in China, inside of China. And then I had the model siting and to of the welfare of a system of a province, uh, and then find the different details of the model, and then apply them my result. And that's me. And hope and looking forward to your advice. Thank you.
That was fantastic. That was so illuminating. I've got a couple of comments as well as questions that I thought I might kick off before I open to everybody else to help just spark the discussion. I think the point that you've picked out on about this free riding sort of intranational as well as international is really important, and the fact that you've tackled this from an empirical point of view is very commendable. It's interesting, some of the problems that you identified across China being so large, across sort of free riding on East versus West, reminds me of some of the problems we also face in Australia, being a very large country, and the West Coast, by virtue of their resource endowment, are generally more emissions producing than, for example, the East Coast. So I guess my question to you is, do you see this free riding problem only existing in larger countries or continents like Australia or China, or do you see this being less of a problem when we look at places like, for example, Norway or New Zealand, where they're much, much smaller?
All right, so I think the free riding in the climate change is like, the function, the decision functions for the government, it's the cost benefit function of the government. It's only the cost and benefit. It's from the money side. It's from the bank. It's but they didn't take into consideration of the climate. So it doesn't matter the size of the country. It's like maybe in China, like the east side, they are producing like economy from the computer. On the west side, they are producing the economy from the coal, from the gas, and the one is polluting and the one is that. So the free riding is occurs. Some of them they get benefit of the clean air, but some of them they want to improve their welfare. They have to make pollutions. It's everywhere. We can, if the mechanism of the free riding, the club system can be applied, in the small region and in the international agreements. It's the same. We can try to, but they have lots of things we have to take into considerations. And the model is a huge stuff, and the stuff you have to figure it out in the next time.
And yeah, you're very lucky with the provincial level data that is available in China, that you can actually undertake such detailed analysis. So congratulations. Can I open it up to anybody else within the session that may have questions? You can ask them verbally, unmute, or put them in the chat. No more questions? No? Okay, well, thank you very much, Yufan, for an excellent presentation. That was a great contribution, and please make sure your slides are uploaded so that all of the participants are able to access them after your presentation.
Yep, thank you so much, and looking forward to your future questions.
Excellent. So I'll ask you to stop sharing screens now, and we'll invite Hendrik to join. So Hendrik is going to be presenting to us on the rebound effects of electricity prosuming in Germany using a matching approach. So Hendrik, I welcome you aboard. I'll mute and hand over to you.
Okay, thanks a lot. So yeah, thanks for the introduction. I guess and hope that you can all see my screen now. So yeah, if not, just let me know. Okay, so yeah, as Kelly already mentioned, this is some work on the rebound effects of solar prosuming in Germany. This is joint work with Tugba, Atasoy, and Madlener, who are my co-authors, and this is also still very much work in progress. So your comments are much appreciated. So what is the main idea, or this sort of the central question that we started with? So in Germany, as in many other countries, solar PV systems or solar electricity generation has seen a strong rise in terms of the volume and its contribution to the energy system. And of course, in Germany, especially, this has been facilitated by quite generous tariff schemes and subsidies and so on, which from an emissions point of view is of course quite beneficial because it substitutes the non-clean energy from coal and gas and so on with clean solar energy. But there might be some unintended consequences and effects on the behavior of those households that implement solar PV, which is exactly what we're looking at here. So there might be some sort of rebound effect caused by presuming, meaning that those households that implement solar PV, so they move from consumers to prosumers, they might then use more electricity, use more energy due to a variety of causes. And that, of course, would constitute a sort of rebound effect. And also just to sort of clarify, so presuming in this case refers to the practice of producing your own electricity while still being a consumer as a private household. And also we only look at solar as the source of presuming. Of course, there are other ways to be a presumer as well. So our two research questions then are first to quantify this difference in electricity consumption between prosumer and consumer households, and that difference would then, by our definition, be a rebound effect caused by presuming. And then secondly, also what are the mechanisms that actually explain those differences and that cause those differences. So it might be because of different price and incentive structures. This is also the focus of this presentation mainly, but there might also be other reasons. Maybe there are different attitudes and perceptions about environmental issues, different awareness, for example. There might also be differences in sort of the technical equipment that people have in their homes, such as smart meters. So there's already some research on that first question, on the extent or the magnitude of this rebound effect. Generally, the literature finds somewhat modest effects that are sort of in the range of 20% or less. And here in this third paper, Oberst and others found that actually also with the matching approach, that after matching, there was actually no difference between prosumers and consumers. And also just for transparency, I was also a co-author on this study, but it had a sort of a different approach and different research question. So we do look to provide some more empirical evidence on this first question, and for the second part of the question, the causes of the rebound, there's not really much or any sort of systematic research at this point that we know of, but it certainly is somewhat of a growing field of literature. So there are quite a few new studies coming up and that have been introduced in the last couple of years, especially. So The main issue here, if we really want to find some sort of causal effect, is of course that you can imagine implementing solar PV in your own home is not something that is assigned randomly, but people actually consciously make that choice. So this can of course lead to selection bias in the sense that if you decide to implement PV, you may already be a different type of household than those that don't, and that might also cause the difference in the energy consumption. So ideally, you would have some sort of randomized control trial where you just sort of randomly pick different households and assign solar PV systems to them, and then just look at the differences, and then you would have a control group as well. But obviously, for legal and also ethical reasons, this may not really be possible in that sense, because you cannot just randomly install PV systems in different homes. So we sort of use the next best thing, which is the propensity score matching approach, which sort of tries to recreate a randomized control trial using observational data. And just briefly, maybe you're also familiar with this type of method. So the way this works is, as I said, you can use observational data on the treatment and control groups. In our case, that's the prosumers and the consumers. You then try to sort of equalize those two groups. So first you reduce the dimensionality of the different covariates to a single value, which is then in propensity score matching. That's what the propensity score is. We define this as the probability of being in the treatment group. So that's just a score between 0 and 1. And that's explained by the other variables, such as, for example, income, the size of your home, the number of people that live in your home, and so on. And everything that has an influence on being a presumer or not a presumer would then be part of that propensity score. And that, of course, can be estimated with a logit or probit regression. And then once you have that score, so that every observation has this propensity score that's between 0 and 1, and then you match each treatment observation to one of the control observations, and you always match the ones that are the closest to each other in the propensity score, because those are sort of the most similar observations from each group in that sense. And then everybody who does not have a match from the control group, because the control group usually is much larger, is then dropped from the sample size, and the remaining sample would then be much closer in terms of their distribution of the covariates. Right, so the idea then is that this reduces the selection bias. So in the perfect case, you could say then if it works perfectly, the two groups are completely similar. They're identical, except that some are prosumers, some are consumers. And then if there's still a difference in the consumption, you could argue that that difference is caused by the treatment, because there's nothing else that could explain it, because everything else is equal between the groups. That's sort of the perfect case, which of course in reality does not really work that well, but that's sort of the principle. And yeah, just to give you a sort of a quick visual example that maybe also helps to explain it. So imagine we have this number of observations here, some are in the treatment group and some in the control group, and we can see the propensity score and then the outcome. So the outcome in our case is the electricity consumption, and then we would just always match those observations that are the closest to each other in the propensity score. So the difference in the propensity score is here in the blue line, and then the red lines are then the differences in the outcome between those matched observations, and that would be our treatment effect, or like the average of those red bars would then be the treatment effect, and the gray observations from the control group, they are just dropped from the sample because they don't have a match that is close to them. So as I mentioned, you can use observational data for this. So we designed and conducted an online survey in early 2020 in Germany. So we only asked, in this case, homeowners. And we had, of course, both prosumers and consumers in our group. And the survey is also representative in terms of age and geographical distribution for Germany. And yeah, we had a variety of questions here regarding things like the way people are informed about their own consumption. Also, if they know their own consumption, we ask them to estimate. Also, importantly, about prices, about their consumption level. So we ask people to actually look at their electricity bill and give us the information that they have there on prices, on how much they pay, how much they consume, and so on. And also, of course, for the prosumers, how much they feed in, how much they received in terms of, and also and so these variables cannot be used in matching.
Hendrik, sorry, I think we lost you a little bit. I don't know if you can approach the microphone. It's a sound problem, or
you can get closer or speak a little louder. Maybe.
Better.
Okay, great. Yeah, as I was saying, so all those variables can be used in matching. So in principle, we have to include everything in matching that influences the treatment or control decision or distinction in order to reduce the selection bias. And just to give you like a brief look at some of the descriptive statistics, so this is not all variables that we included, but just some of them. You can see here the mean of those variables in the treatment group before the matching, and then after the matching, after we drop some of the control observations, so not a good match, we can see that for most of these variables, now the mean is closer to what it is in the treatment group. And the treatment group, of course, is the same before and after matching, because we don't drop anybody from the treatment group, we just drop from the control group in order to get a closer, to have two groups that are closer together in terms of the distribution of the covariates. Just to give you one example, we see that in terms of living space, prosumers, apparently they have bigger houses, bigger homes than the control group observations. But after the matching, we see that now the control group also has, basically they have bigger homes, so they don't have a closer match.
I'm so sorry, Hendrik. I must interrupt. I'm still struggling to hear you clearly. It just all of a sudden dropped off, and I think a few people are having issues.
Okay.
And we've got a little bit of spare time, so if we can possibly rectify that. I know sometimes switching the video off improves the connection, as much as it's lovely to see your face. If that's, I'm not sure if that's a workaround that might help.
Yeah, or we can try this headset. I don't know if this is going to work. Is this better? Can you hear me now?
Yeah.
Okay, great.
Perfect.
Okay, nice. Yeah, I guess it's good to be prepared. So yeah, let me just briefly repeat that last part. So for example, as you can see here in the mean in the treatment group for living space, so that's in square meters. So we can see that the treatment group, apparently they live in bigger homes than the non-prosumers, as you can see by the difference here. But then after the matching, after you drop some of the control observations, the ones that are not a good match for the treatment group, we can see that now the control group also has a mean living space that is much closer to the treatment group. And that is sort of the idea that after the matching, the distribution of between the two groups in the different variables, is much closer to each other. So the groups are more comparable now. It's basically what the goal is of the matching. And also just another sort of visual representation of this. So here we can see the difference between the two groups in percent in this case. And the dots are for the unmatched case for all the different variables, and the X's are for the matched case. So since, and of course this is not formal proof or anything, but just visually you can see that the X's for the matched case, they are much closer to the 0 line. So that means the bias or the difference between the two groups in percent is also strongly reduced for, not for all of the variables, but for most of them, which is also a sign that the matching actually works as it's intended. And yeah, moving on to our first results. So we, as the outcome, we always have the yearly electricity consumption in kilowatt hours, and that value without any matching would be around 4.1 thousand kilowatt hours for prosumers, and for consumers it's 3.6. So that's the difference without matching, and that difference is, as you can see here, also statistically significant. So without any matching, if you just compare the two groups, the prosumers consume significantly more. But after the matching, which is what you can see here, that's the average treatment effect on the treated, that difference is smaller, and also more importantly, it's no longer statistically significant. So what that means is that the prosumers do consume more electricity, and this of course includes self-consumption. They do consume more than the consumers, but if you control for the difference between the groups in terms of, as we saw, also income, living space, number of people in the home, electric vehicles, and all the other variables that we match on, those differences diminish. So that sort of suggests at this stage, this is still preliminary, but at this stage, this would suggest that, yeah, it's not the prosuming that makes people consume more electricity, but it might be something else, some other explanation there. Which would also suggest that at this point there's basically no rebound from prosuming. Now, sort of moving on to also the second question that we have, which is mainly the effects of the incentive structures. This is sort of a simplified cost function for electricity. So as a consumer, basically the amount you pay for electricity is just determined by the electricity price P and the amount you consume from the grid, because that's the only place you can consume electricity from. As a prosumer, you also have the second part, at least if you have a feed-in tariff, as is the case in Germany. So if you have a feed-in tariff, but you self-consume that electricity that you could have fed in, that means your opportunity cost would be then exactly the amount of the feed-in tariff, because you could have fed that kilowatt hour in and received the feed-in tariff T, but if you didn't and you consumed it yourself, then that means you have that opportunity cost. So now, of course, what's interesting here is if the relationship between T and P. So in the case that the feed-in tariff is higher than the actual electricity price, the incentive would be to always feed in everything, because you can make more money by this, and then just consume whatever you need from the grid, because that, at least from an economic point of view, that's your incentive. In the case of T smaller than P, the incentive would then be to first of all maximize your own self-consumption, but you also have an incentive as a prosumer to consume more in general, because the consumption is now cheaper than it would be for a regular consumer. Up to the point where you just self-consume everything that you produce. Of course, from that point on, you can only consume from the grid again, and then that would of course change. So this is quite important to see the distinction if T is larger or smaller than P, or what the relationship is between the two, and how it might change the incentives. And to show you this graph would also maybe help explain this further. So the prices and the feed-in tariffs that we have is they are always from 2020 or 2019, which is when we conducted the survey. But the years that you can see here, that's the installation year of the PV system. Now the installation year has no influence on the electricity price that people pay today, obviously, but it still makes a difference on the feed-in tariff, because that's the way it works in Germany, where the feed-in tariff is guaranteed for 20 years based on the installation year. So that means if you installed your PV system, for example, in 2005, you would get a feed-in tariff that is around right here, like 55 cents maybe per kilowatt hour, which is quite generous. And you still receive that money today if you feed in today. And you will continue to receive it until 2025, of course, because it's fixed for 20 years. Now, of course, your electricity price today is around 30 cents. And that, of course, has is not dependent on when you installed the PV system. But what we can see from this graph is then that if you installed your system somewhere around here before 2011, then it would be quite profitable for you to feed in 100% of your generation and just consume what you need to consume from the grid, because that sort of maximizes the profit that you can derive from your generation. But as you can see, the feed-in tariff was then reduced quite significantly. Okay, 2 minutes left. Thanks. Around 2010, 2011, there was this sort of cutoff point where now it's actually more profitable to self-consume everything you can, because feeding in is not really profitable anymore. As you can see here, the feed-in tariff is now around 10, 12 cents per kilowatt hour, which is a lot less than the electricity price. So now the incentive is to self-consume as much as you can, which may also then lead to the effect of people just consuming more in general, depending on if the self-consumption is then a substitute for the regular consumption, or if people just add it on top of their regular consumption, which is kind of the interesting question here. And so to check for this last part, we did the matching again with the subsample. So this is just the table from the full sample before, and then we divided this by the PV installation year in 2011 or earlier, and then after 2011. And as you can see, especially here, that if the PV system is installed after 2011, then in that case, the prosumers consume quite a lot more, or significantly more than the consumers. And this is also an effect that is persistent after the matching, as you can see here, and it's also highly statistically significant, unlike in the case of the full sample. So this, again, this is preliminary, but this would suggest then that this incentive structure causes the prosumers, especially those with the lower feed-in tariff, to self-consume more, and to also add that self-consumption on top of their regular consumption, because their total consumption is now much higher than it is for the consumers, and it's also after matching still higher than it was in the other case with the full sample. So just to conclude, we have basically two main results here. So if we just look at the full sample, we don't find a rebound effect based on these estimations. But what we do find is that the lower feed-in tariff may cause not only the incentive to self-consume a lot, this is sort of the more trivial part, but also increase the incentive to consume in total, which may or may not be what the policymakers would like to avoid, of course, because in general, of course, the goal is to reduce electricity consumption, even though that electricity consumption from prosumers is, of course, emissions-free, but still, as a policymaker, might want to avoid this sort of excessive consumption. And yeah, there's still some things left to do, like all those other factors that I mentioned, like perceptions, attitudes, and so on, would be interesting to explore further. And of course, the question is then also, what does this mean for the feed-in tariff? Should the feed-in tariff be higher just to avoid this type of excess consumption? Because that would also be quite expensive for a public policy point of view. So that's, I guess, still an open question. So with that, I'm happy to answer your question. Yeah, this is the reference for the working paper that is not quite available yet, but we'll soon get there. So yeah, thank you for your attention.
Thank you very much, Hendrik. That was a fantastic presentation. Very illuminating. This time I'd like to open it up to the participants. We've sort of got over a dozen people in the room at the moment. So I certainly have a couple of questions and comments, but I thought I would open it up to anyone else in the room if they would like to speak verbally or open through the chat to ask any questions to Hendrik. Don't be shy.
All right, so can I ask you a short question? Like, I know once from the Jesse, who is a professor in the Corona, and he did some environment experimental test to see how the behavior of people make use the electronic in the different time of the day. So do you have any ideas like the systems for the feed-in craft, feed-in tax? What's the effect of that to the people's consumption of the electronic in the different time of the day? Do you have any sense to understand this topic?
Yeah, I mean, we don't have any data exactly on when the people use electricity. We only know the total. But I mean, what you say, I think that's a very good point, because it certainly has an influence on how much you can actually feed in and how much you can actually self-consume. Because of course, the load profile usually is set up in a way that you have these like spikes in the morning or in the evening, or both usually. But the generation is usually highest during noon when the sun is shining, when the sun is the highest, right? So that I think has a lot of influence on how much you can actually self-consume if your goal is to maximize the self-consumption. So that is something that we're trying to figure out how to also implement this, or what effect this might have. But unfortunately, we don't have the exact data on the time of day or when people are actually using their electricity. But we do have some questions in the survey where we ask people about their behaviors, like whether or not they change their behavior now because they are now prosumers. So they, if they maybe change their behavior also to maximize the self-consumption, but we don't have any sort of quantifiable data on this. And it also, of course, it's related to this question of storage, which also we have not really looked at in detail, because storage might also change the whole picture, of course. Yeah, I think it's a good point.
Have you control for the weather, difference in the weather, like the rain, the sun? Have you control for the day, the percentage of the days in the sunny day and the shower or something? Have you controlled this?
No, we have not, because the data is just based on 2019, basically. So at this point, we would argue that the weather effects are the same for everybody, but of course there might be regional effects, right? Because there are of course differences in geographical location of the people, and then the sun is shining more or less in different places. But we could control for this, yeah, and we should actually, yeah. That's, I think, a good point.
That's all I have. Thank you.
Well, thanks a lot.
Hendrik, can I ask you a couple of questions?
Sure.
How do you know how much the prosumers are self-consuming? How does that work in your region?
So
in Victoria, we don't have any capacity we know what they feed into the grid, but we don't know actually. We've had to develop a way to try to estimate it. So I'm interested to know how much, like how you figured that out.
So yeah, I mean, it depends on the scheme, and it always depends on the installation year, because that's always sort of the deciding factor, like under which regime your system is under. But usually people also get a bill for their self-consumption. Not everybody, because it kind of changed over time, but yeah, that's mostly how we figured this out. Yeah. So if they feed in, of course they get a bill because they get paid, but also for the self-consumption, they usually also get a bill from their provider. There was also some point in time where you also had to pay for your own self-consumption. So the regulations changed over time quite a bit, but for at least for the largest part of the sample, we have people at least told us, what's on their bill in their self-consumption. Of course, we have to assume that they know what they put in, they are telling the truth, and so on.
Yeah, it strikes me how different it is across the world. I mean, even these guaranteed feed-in tariffs that you have for 20 years. I mean, it just strikes me how different the policies are around feed-in tariffs and prosuming, and it's been a very illuminating.
Can I just ask? I'm
sure.
Not sure if you can hear me.
Yeah.
Oh, okay. So just coming back to Kelly's question, that must mean that there's gross metering. So you meter the solar production from the customer. It's not a net. It'll obviously be the purchases to and from the grid, but there's also a metering of the solar production.
Yeah, so in Germany, this is also maybe a bit more complicated than in other countries, but in Germany, there's actually the choice to have gross or net metering. That's the choice of the household, and they can also actually switch between them.
But I'm not clear. If it's not gross metered, how do you know how much electricity is used on the premises?
Well, yeah, I mean, what we did is we asked the people either if they have some sort of bill from the provider that tells them about their self-consumption, or if they track their own self-consumption, because a lot of people also do this. But of course, you know, this might not be as accurate as an actual bill, but that's how we try to track this, yeah.
Right, but what I'm not clear is even those customers that track it, they can't know how much of their own solar they use unless they measure their own solar production every day and their own consumption every day and their grid purchases every day. Because if it's not automatically metered, those 3 bits of information they have to have so that they can tell you.
Yeah, I'm not quite sure. So, I mean, they know how much they feed in because they get a bill for that.
Yep.
They know how much they consume from the grid.
Yep.
But
yeah. they can't know how much of their own solar they self-consume unless they know how much their solar produces every day that they consume.
Yeah, that's right. Yeah. Yeah, that's true. I mean, we could estimate the production because we also asked for the size of the system, that we could try to figure out at least roughly the actual production over the year.
That's hard. That's really hard. It's really hard to estimate that. And I'm thinking, I mean, it's hard here where we've got seasonal variation. I should think it's extremely hard there with a much bigger seasonal changes. So that must mean that you've got measurements of gross solar production. That's very interesting. That's not actually measured here in Australia.
Well, that's what I'm trying. I'd like to go back to slide 12 and variable S that you had on slide 12, if we could, Hendrik. So that variable S, that self-consumption amount, how did you measure that exactly?
So yeah, that is measured either. I mean, first of all, we asked people, do you have self-consumption at all? Because some, as we saw, some just feed in everything. They don't even have self-consumption, so then it's just 0. But for those that do, they either have a bill from their provider that says the exact amount, because as I said, in some cases, there might be like they have to pay levies on that self-consumption also. So it has to be built in some way. And if not, then we ask people, do you track your own self-consumption? And as it turns out, actually, sort of a majority, at least, of prosumers do. There are some where this is not the case, and then, yeah, of course, those observations are basically lost, or we have to deduct them. This might also influence, of course, the composition of the sample, because there might be an effect of those that are very aware of their own consumption and so on. But this is sort of the best we could do. So it's either on the bill, or we ask people, do you track your own consumption? And actually, a lot of people do that. Yeah.
Yeah, that is very interesting. It means that in Germany there's gross metering of solar production, and that's known. That must be known by the customer if they're going to track it themselves, or known by the energy retailer so that they can bill for it. That's very interesting.
Yep.
Were there any other questions for Hendrik from the attendees in the session? Okay, well, thank you, Hendrik, for a very illuminating presentation. I suspect there might even be a follow-up email from Bruce and I to you at some stage.
Yeah, looking forward to that. Thanks a lot.
So I'll ask you to stop sharing your screen now, and I will pop mine up. Is everyone able to see the introductory page slide? Fantastic, that's great. Okay, so the title of my presentation today is Wholesale Price Pass-Through to Retail Electricity Prices in Liberalized Energy Markets. It's specifically a study of Victoria, Australia, and I've undertaken this research in collaboration with Professor Bruce Mountain, who also did a presentation yesterday on solar PV, which is sort of related to some of the things that we were sort of just discussing with Hendrik as well. Okay, so just to give some background and introduction. So in the 1990s, wholesale electricity markets were introduced in the state of Victoria in a very similar approach as they'd been introduced in other places around the world, such as Britain. 10 years after that, we had retail electricity markets being introduced in Victoria. And it's been a huge transformation in the last sort of 30 years. We now have around 30 electricity retailers just in the state of Victoria. And at any one time, there's over 200 tariffs that are actually available to a consumer, an average household in the market. Retailers in Victoria are free to set the prices, and the prices change very, very frequently. The government has taken a very active role in trying to promote consumers to search and to switch for the best possible offer available to them, so that all of these benefits of competition can actually be realised. The Victorian government also established what's called the Victorian default offer. And it's a very similar to what has been introduced in other sort of competitive, liberalised retail electricity markets around the world, where the government regulatory body basically sets a default offer, a reasonable price that needs to be made available to all of the retailers. And there was a second addition to this Victorian default offer in Victoria, which also required the retailers on all of the bills to actually tell their consumer, their customer, whether they offered a better deal for them. And that's required to be reported on every bill that is actually supplied to the customers. And so the policy objective around these search and switch encouragements and the government-run comparison website and the Victorian default offer was really to help reduce bills, particularly for customers that might not necessarily be engaged, but also to help promote customers to be engaged. So this project is really around assessing whether competition has worked in Victoria and whether this Victorian default offer has actually achieved what the government hoped it would achieve. Okay, so in liberalised energy markets, the whole concept of pass-through is that competition will mean that wholesale price movements are actually reflected in the retail prices. And so there should be this efficient pricing where, for example, as we see increasing renewables coming into the generation market that are subsequently reducing those wholesale prices, we should be expecting to see those pass through into household bills. And this concept of competition in like freely competitive markets, meaning that wholesale prices will pass through to retail prices, has been examined across a range of markets, from gasoline to milk to shoes to all sorts of things. And it's certainly been researched in the electricity markets. There's been a lot of research done in this area in the United Kingdom, as well as the Netherlands, Norway, Texas as well. Victoria is relatively new to the analysis of this game because we were a little bit later in terms of liberalising our markets and sort of getting our research expertise and data available to undertake some similar analysis. Okay, so what does the evidence on pass-through in retail electricity markets across the world currently tell us? The findings, look, they range because the markets do have inherently different characteristics. So sometimes we see wholesale prices completely passing through to retail prices, and sometimes they don't completely pass through. And that can depend on the type of retailer or the type of regulation or a range of other characteristics. There's also a lot of evidence that pass-through is asymmetric, meaning that if wholesale prices go up, retailers generally pass that through a lot more quickly and a lot more completely. But if the wholesale prices come down, there's generally evidence that the retailers might not completely pass that through and might not pass it through as quickly as an increase, meaning they're effectively capturing profits in what should be a perfectly competitive market. There's also evidence that pass-through from wholesale to retail prices is dynamic, meaning it doesn't happen straight away. It can take anywhere from 1 to several months for these retailers to actually pass through these wholesale price changes. And this degree of pass-through and asymmetry, again, it depends on so many factors. The regulatory environment, the market share of the retailers, are they incumbents? Are they new entrants? It also depends on consumer loyalty and the search and switching costs that are associated with all of these different markets. So we would expect to see some differences in how these liberalized energy markets have been effective in passing through particularly the wholesale electricity cost declines to retailers. Okay, so what are our research questions? If the liberalisation of Victoria's retail electricity market has been effective, then we would expect to see wholesale prices to pass through to household bills quickly, completely, symmetrically, and there to be without difference across our retailers or our offers. So we specify 5 main hypotheses. The first hypothesis is that the pass-through is dynamic. Okay, so it is going to happen, but it might take a little bit of time. It might happen instantaneously. The second is that the pass-through is complete. If our market is working competitively, we would expect complete pass-through. Hypothesis 3 is that pass-through is symmetric. We would be expecting retailers to pass through increases as well as decreases in their wholesale electricity costs the same way. We want to make sure in hypothesis 4 that there's no difference in the pass-through. Is there any market power that's being exploited by incumbent retailers such that they're not passing through wholesale costs, unlike the new entrants? And hypothesis 5, did the VDO achieve its policy objectives? The setting of the VDO was really meant to help lower electricity bills, particularly for those consumers that weren't necessarily engaged in the market. So there are 5 main hypotheses. Okay, so this is our main approach. There were sort of 7 main steps. And the first 2 should certainly not be underestimated. The first one in terms of how we actually measure wholesale electricity costs was actually quite a difficult issue to tackle, as was how to truly measure electricity prices paid by the households. We had to consider all the other relevant variables that might impact retail prices. We had to review all of the data and consider, what might be an appropriate way to analyse this. And based on that, then review the model specifications and appropriate functional forms. And then we've estimated both symmetric and asymmetric models and then undertaken a range of hypothesis testing so that we can address those 5 main hypotheses. So in terms of measuring wholesale electricity costs, it's basically impossible to truly know what these are with certainty, and it's almost impossible to estimate. The reason is that retailers undertake different hedging strategies to protect themselves from movements in the spot price. So in fact, retailers rarely pay the spot price in the market because they are fully, if not overly, hedged. And we considered 4 different methods of estimating wholesale electricity costs. That included spot prices, looking at quarterly future prices, and that was looking at the forward future 12-month supply period. We also used, I looked at a representative hedging strategy that was actually used by the Victorian regulators in setting the VDO. And we also looked at a representative hedging strategy that was used by one of the retailers. And we reviewed all four of these, and really number 2 was the only one that worked for us on a monthly basis. The first one, as we know, is not realistic, and 3 and 4 were designed to estimate an annual wholesale electricity cost, not a monthly, so it just didn't meet the pub test. So, as I said, we stuck with the second option. So we used a simple weighted average of the forward-looking quarterly base futures prices. They were trade weighted volume prices, on the assumption that if a retailer took a consumer on now, what price would they set now based on what those future prices to supply for the next 12 months would be, based on a 12-month weighted price as to the trades up to that point. So it's as representative as we could possibly come up with, but obviously welcome to comment. In terms of how we measure our retail electricity prices, we are very lucky. We actually have a sample of around 50,000 actual household electricity bills that have been read in PDF format. We don't have to estimate anything. We know exactly how much they're consuming. We know their discounts. We know their concessions. We know their solar revenue. And we can, we've actually reviewed the sample of bills that we've received, and it is very much representative of the population. So it's important to remember when we're looking at electricity prices, there are various components of those, and the largest component is actually the network costs. And so what we've done is actually exclude those network costs in pricing the retail bills, so that we can focus on what the wholesale electricity costs are, which are about 1/3 of the total household retail bill, with the remainder then being made up of, as I said, the network costs, 38%. And then we've got some environmental costs to meet our national renewable energy targets, and of course, the retail margins. So we take these 50-odd thousand bills and we price each individual bill across all of those 200 offers. And then we select the median offer at the 10th, 50th and 90th percentile. And that's a very consistent methodology we've used in previous research. We look at the 10th, 50th and 90th percentile. So they're the cheapest, the median and the most expensive offers across all retailers and then across retailer tiers. And we describe the retailer tiers as the tier 1s being our incumbents, our major 3 that were there when we first opened up the markets. Tier 2 have customer share between 3 and 10, and tier 3 less than 3%. We looked at a range of other variables: labour costs, spurious results, and customer switching rates again did not add. And in fact, the Granger causality looked the other way. We did, however, of course, include a dummy variable account to account for the Victorian default offer. Okay, so to look at what we've got here, this is the 10th, 50th and 90th percentile offers that we have in the top 3 rows here. These are the wholesale electricity costs, and this is the point at which the VDO occurred. So you can see there's definitely been some differences across the cheapest offers as opposed to the most expensive offers, particularly at the introduction of the VDO. When we look at the median offers, these are actually the median offers, again, you can see that they've actually all increased around this time, although not a lot of change in some of the instances. Oops, sorry, here we go, that's the 50th. I do apologise. That's all retailers, yes. Sorry, I do apologize. This was the most expensive, the median, and the cheapest for all retailers. And this here is where we just look at the cheapest offers by all retailers. This is the median offers by all retailers. And then these are the most expensive offers by the retailers. And so you'll see here the most expensive have very much come down, which is in contrast to what we saw with the cheapest offers. And so we're really trying to uncover here about how the impact of the VDO, as well as movements in the wholesale electricity costs, have related to these differences in the trends that we've seen. What's interesting when we look at the correlation is that we generally do see a high and overall positive correlation between the wholesale electricity costs and the retail prices. But interestingly, we do see negative correlations for some of the middle tier retailers in the median offers, and also some of the cheapest offers. But the highest correlation comes between your tier 1 offers. So this is what really warrants further investigation. Excuse me. Excuse me. So we undertook unit root tests of all of the variables. Overwhelmingly, all of the variables have evidence of stationarity, no evidence of co-integration. And on the basis of this, we fit a symmetric and asymmetric ARDL model to each tier and each percentile, present our model diagnostics, and then make a final model selection for our hypothesis testing. This is a description of the ARDL model. So we have the lag dependent variable, and then we have the lagged wholesale electricity prices, and we've also got the dummy. And then we have a similar asymmetric where the value of the wholesale price depends on whether it's had a positive or negative decline. Okay, so let's just move right along. So in terms of the model diagnostics, we know prima facie the wholesale prices are a component of the retail cost component. So we know that we're not going to get a spurious causal relation. When we evaluate the estimated coefficients, they're very plausible in terms of a sanity check on what we observe in those graphs. We find no evidence of co-integration, and the model diagnostics are very desirable overall. And the sensitivity analysis was also very promising. So after we did the sanity check, the model diagnostics, we also did a non-nested model selection test to figure out whether the symmetric or the asymmetric model would fit better. So I won't bother you with the diagnostics, here they all are, but based on all of that, what their final models that we rested on here, for all retailers, as we see here for the 10th percentile offers, we had a asymmetric model for all, an asymmetric for the T2, and an symmetric for the T1 and the T3. So just to give you a summary of what these results actually tell us, what we can see here is that the VDO had a statistically significant impact on all of the offers across all of the retailers. And it actually increased the T3 retailers the most. When we look at the pass-through, so we can see here the pass-through, for example, here, and also here, and also here, and here, here, and also here. So we can see that in general, the T1 has incomplete but symmetric and immediate pass-through. T2 appears to have incomplete but immediate pass-through, but there's some asymmetry in the rate, with the price increases taking longer to come through than the decreases. And with T3, we see there's complete but symmetric pass-through, but it actually takes 4 months to come through. So there's definitely a lot of differences there. So when we move through to the 50th percentile offers, again, they all generally pass the model diagnostic tests, and the models that, that we rest upon finally are presented here. And what we can see is that the VDO across all offers in the 50th percentile didn't have a significant impact. But it did have a different impact across the different retailers. So for example, the tier 1 retailers actually reduced their offers with the VDO, but tier 2 increased, and yet tier 3 had no impact. And in fact, we see also differences in terms of whether the pass-through is complete or symmetric. And we do further testing, as I'll show you in the next few slides. In terms of the 90th percentile offers, again, generally the model diagnostics were fantastic, and these were the final models that we relied upon. So for all retailers, we see here the VDO reduced the most expensive offers, and we see that consistently across all of the different offers of all the different retailers. But again, we see that in T1, the pass-through seems to be incomplete, but with T2, it seems to be complete. So again, we're seeing these differences in the pass-through. So to give you a summary in terms of our hypotheses, in terms of H1, is pass-through dynamic? We see across all retailers, it takes a lot longer for pass-through in the 90th percentiles. And we see in T2, it does take a little bit longer, particularly for the 10th and the 90th. And Tier 3 take a lot longer in their 10th. So the pass-through is very different across the retailers and the offers. In terms of whether the pass-through is complete, the red areas here, or the shaded red areas, indicate where it's not complete pass-through. And so we see here the T1 retailers across all of their offers don't pass through completely. The Tier 2 retailers do not pass through completely on their cheapest offers either. The Tier 3 incomplete pass-through is really explained by the fact that there's not many customers that are taking the most expensive offers from Tier 3 retailers whatsoever. When we look at the confidence intervals for the pass-through, again, we see the T1 retailers, the incumbent retailers, are not fully passing through. And again, the Tier 2 retailers with that market share between 3 and 10% are again not passing through. When we look at asymmetry, no evidence whatsoever. Okay, there's no evidence that the magnitude of the pass-through between the increases and the decreases differ whatsoever. And in terms of hypothesis 4, does the pass-through vary? As we've seen, the pass-through varies significantly between the magnitude and the time and the completeness across both retailers and offers. The VDO, as we saw, it had a significant impact, but that impact varied. It caused the retailers to withdraw their cheapest offers, pushing the cheapest offers up, but it pulled the most expensive offers down. So that's a summary basically of what I've just said. In terms of some limitations to our research, we do have a limited sample size. It may explain why we found no co-integration and may explain why there is incomplete pass-through found sometimes. And in terms of the market does evolve when we get more data, our conclusions may change. And as we explained, the measurement of retail and wholesale prices is very difficult. And so that could also impact these results. So finally, conclusions. These relationships between pass-through vary widely. But in Victoria overall, I think we can see that excluding the incumbent retailers, we are seeing very good pass-through from wholesale to retail prices, which is very promising. But there's still this question about why consumers are remaining loyal to incumbent retailers and not achieving these wholesale price declines. And unfortunately, it looks like there's been a VDO policy failure. It looks like it's been set too high, which is what's caused the retailers to withdraw their cheapest offers from the market. So controversial findings, and I welcome any questions or comments.
Thank you very much, Kelly. If anyone has a question, this is the right moment to do it. The floor is open. You can do it with the chat or raising your hand. Okay.
I might have a question. Thanks a lot, Kelly, for the presentation. Very interesting. I'm just wondering what kind of retail tariff is proposed to the consumer. Is that flat tariffs, so annual price for electricity in cents per kilowatt hour, or there is on-peak, off-peak prices, or even more dynamic prices? Because then the pass-through can depend on each part of the retail price, basically. Maybe for on-peak, there is a complete pass-through and not for the off-peak price or something like this. So have you investigated a bit on this, and can you expand on what's the situation in Victoria? Thanks.
That's actually a very interesting question, and thank you for bringing that up, because I should have pointed that out in the data. So our analysis was on the household bills on flat rate tariffs. Having said that, when we reviewed, as I was talking about those 4 wholesale electricity cost options, the frontier economics approach did actually look at a fully hedged position for a retailer supplying both during the peak and the off-peak period. So our analysis is based on households on flat rate tariffs. But from what I've seen, I don't think we would see a significant difference, because the retailers are so fully hedged, and they're reflecting that in their retail prices, as we've seen in the results. Yeah. But I'd be happy to certainly discuss that more with you.
I have another question, Kelly. Is it, I don't know the variability of the energy prices in Victoria, but is it possible that you have any sort of source of exogenous variability that can make more cautious the retailers to hedge more long-term or something like that? For example, the scarcity of water for hydro and so on.
You know, that's a very interesting question, and something Bruce and I have been talking about lately, because the wholesale electricity costs. So if you had a graph of the spot price and then the weighted quarterly base prices that we had, if you looked sort of up to sort of January 2019, spot prices were above those hedged simple average prices. It's now gone the other way. So in fact, retailers would be better off now not hedging at all, than taking on a hedged position. So there's definitely, we're interested in monitoring the trading logs, because that significant decline in the wholesale electricity costs should definitely change the hedging behavior of the retailers, which then will change their wholesale electricity costs, which should translate into changes in our household bills. But again, we just don't know what they're actually doing. So you would anticipate a smart retailer would be hedging less, but whether they are, and we've looked at the figures, retailers would have been much better off not hedging than hedging necessarily, excluding those times, obviously, when the spot price sort of exceeds $300. And Bruce, I'd welcome you to add to the discussion.
Yeah. Okay. We have extremely high electricity prices that they can rise to extremely high levels, up to $15,000. And so retailers will go out of business overnight if there's a few settlement periods in which prices reach those levels. So typically they'll hedge through generator ownership or through contracts, but they can choose a hedging strategy in a range of ways, hedging the capping their exposure to those extreme prices, but accepting the spot price that flows under that cap. So hedging strategies can be affected, and as Kelly points out, they'd been a lot better this quarter if they didn't hedge, but we just need a few events. A coal-fired generator, as happened in the last week, blow up, and suddenly we get $15,000 a megawatt hour for 5 minutes or for 15 minutes, and retailers lose a fortune.
Thank you very much. There is a question in the chat from Jilun Lu. The question is, hi Kelly, thanks for your presentation. I was wondering, are retail prices menu diverse in Australia? Since I did some studies in Japan, although it is liberalized market, the menu among all retailers just have very tiny difference.
Yilun, thank you very much for that question. That's actually really interesting. So in our research, we have discovered such a wide variety of tariffs. And as we said, there's over 200. Prices can differ so significantly. We do have the flat rate tariffs and we have the time of use tariffs. And then of course, if you've got solar, then those feed-in rates also differ significantly as well. So there is a huge diversity, which is why in our research, it is so important that we get the actual household bill. In a lot of other studies, they say, oh, this is house average consumption and average price. We cannot do that in Victoria, and arguably, I don't think you can do it in many competitive retail electricity markets, although I don't know enough about Japan to speak about that specifically. But this is why the importance of having the household bills is so front of face of our research, because of the diversity. And so I would love to know more about the lack of diversity that you referred to in Japan, because that's very different than what we see here. So I'd be very interested to know more about that. And you can email me privately, that's also fine.
Okay, is there any other question? Okay, thank you very much to all the presenters, to Kelly for hosting as well the presentations. I just remind you that this conference has been recorded and that we will be available in the channel of the conference. So thank you very much, and I hope that we see each other again in the near future.
Thank you very much.
Okay, bye.
Thanks, everyone. Bye.
All right, see you
Thanks.
guys.
Bye.
Take care.
Good day.
Bye.